back one step, okay, and I say that I'm going to impose a decoding order. Okay. So I'm going to do the following thing. I'm going to put a encoder at the beginning here. You draw this thing up. So what I want to do was the following thing. Suppose what I wanted to do was, what we were trying to design was the following. This is the usual communication system that I have, right? This is what I try to do is I take a message, I encode it to some input sequence, the channel maps it into an output sequence, decoder observes this, tries to recover the message. So, what we'll do is the following thing. I'm going to use an encoder here. Encoder minus, let's say. Okay. This encoder is going to take the message M minus, map it into some sequence U1N. This encoder will take the message M plus, it'll map it into a sequence U2N. We're going to take the U2, send it through n copies of W. You want me to switch? Okay. No, empty. A higher contrast. And we take the modulo to some of these two sequences and pass it through another copy of U2. This is a code of length, block length 2n. Okay, maybe I should think of it as like this one. Okay. And then I have now here decoders sitting in here. The decoder observes both the outputs. I'll pass it through a decoder minus. And I'll decode the M minus. Hopefully I decode this thing correctly. Okay, so if I decode this thing correctly, then I can reconstruct this one. Okay? Because once I know the M minus, okay, if it is correct, then I'll know what the encoder would have done to this M minus. Okay? So from this M minus, I can now map this thing back into the U1, an estimate of it, hopefully correct. Okay? And now I can give the same Y's together with the U to a decoder plus and decode the M plus. So if I impose this decoding order, it's a successive decoding order, first decode the channel output W minus. After we have finished decoding the output W minus, then decode the channel W plus. Okay. Then you'll be in your business. Then you can pretend that this W plus channel in fact had the output U1 in here. Now you might say, well, I mean, this is all and well, but you don't really have U1. You only have the estimate of the U1 hat. So let me then go through one more iteration of this thing and describe to you one more object. Suppose that the following experiment. Suppose you have some, maybe I should say one successive coding. Suppose you have a whole bunch of these U's, U1 to UN, and these things influence some observable Z. Okay? The Z in fact is going to be the output of the channel Y1, Y2, up to Yn, okay? A whole bunch of these things. And now suppose you have the following decoder, which is helped decoder. Let me call it a help decoder. Help decoder works in the following way. Okay, help help decoder estimates the U1 from the observation Z. And then estimates the U2 from observation Z. Okay. But he's helped, so some helper, some genie, gives him the value, the true value of U1. This is not the estimate, it's the true U. Okay. As if in this channel W plus. In the channel W plus, you estimate the U2 with the actual knowledge of U1. We continue like this one. We estimate U3 using not only the observation Z, but the true knowledge of the U1 and U2. And you estimate the last thing UN, not only using Z, but the true knowledge of all the U's up to n minus 1. Now the true decoder, the unhelped decoder, I'm going to use this same functions, decoding functions phi, as the helped decoder, but I'll do it the following way. I'm going to estimate different estimates using the same function and the Z. Okay. Of course, I mean, at this moment, we see that the U1 tilde is the same as the U1 hat. So the vis-a-vis the U1, the helped and the unhelped are the same because the helped decoder is not helped at this moment in any U. For the U2, I'm going to use the A2 of Z, but instead of using the true value of U1, we are not helped, we are poor, okay, so I only can rely on my own resources, okay, I'm a poor guy. But I already decoded, I think I decoded, perhaps correctly, or maybe incorrectly, the U1 tilde. So instead of true value of U1, I use my poor man substitute of the U1, which is what I have in my hands, U1 tilde. We continue like this. Now I'll ask you the following question. Suppose that this help decoder, we have a Z, and decode this thing, and you find that you have decoded correctly. Suppose that the help decoder works correctly as worked. Suppose Z is such that the help decoder made no errors. Would the unhelped decoder make an error or not? No, right? Because for such a Z, okay, well, the U1 hat was correct. So the U1 is the same as the U1 tilde by construction. Okay? So U1 hat being U1 means that the U1 tilde is equal to also U1. Okay? So in this case, U1 tilde is correct, okay, which is the same as this one. So the U2 hat is also equal to U2 tilde, but U2 tilde is also, U2 hat is correct, so it's also correct. Okay, so by induction, everything is correct. Okay, so consequently, whenever this guy decodes correctly, okay, this guy also decodes correctly. Okay, so and secondly, the following is also true. If this guy is incorrect, so is this. Okay, because you can take a look at the first time that this help decoder makes an error, he will also make an error that first time by the same argument that he had. So the Z's for which the unhelped and helped decoders make block errors are exactly the same. Of course, it might be the following might be the case that this guy decodes incorrectly, okay, by having, say, 6 symbols which are wrong. Then this might be incorrect by having 60,000 symbols wrong. Okay, that might be a big difference between how many errors you make in these two cases. But if you're worried about the block error probability, okay, these two are exactly the same. Okay? So the helped and unhelped are the same thing. Okay? So as long as you're worried about block error probabilities, no harm in assuming that at the successive cancellation stages, you do have the access to all the correct decisions of the past. Okay? All right?
Well, by argument, actually, the bit error probability could actually be lower.
Lower, indeed, it's possible. It depends on function phi, of course, right? But if I optimize the function phi such that the unhelped decoder works the best way, that phi is maybe not the right thing for the helped decoder. Okay. Our of course, I mean, if we have this structure here, clearly everything is a function of z. Okay? Because all these tildes that we are using as the argument to these fields are in fact a function of z, okay, by construction here. So unhelped I could have written all these things as being some c of the z alone, okay? But this I think makes it very clear as to the difference between the helped and the unhelped decoders, and that they're different, but they're the same. Okay. Vis-a-vis the blocker probability, they're the same. Okay. Why did I do this? Oh yes, I did this whole thing essentially to convince you that this synthetic channels that I have, maybe I have to write them here also. But this construction is in fact legitimate, okay? In the sense that as long as I respect the decoding order, if I decode the channel W minus before I attempt to decode W plus, everything is okay. If I did my decoding in the wrong order, then of course this is not a legitimate construction in U. Okay, so now what about this this notation W minus and W plus? I'm not very good, by the way, with organizing blackboards. Most likely I'll erase things and then realize that I need them at the next second. Okay? But you got to bear with me. I'll have to rewrite the same thing 18 times. It's not too worry. Okay. Now, maybe there's one notation. Vincent was using notation IPW to denote the mutual information between the input and the output of the channel. When the input X is distributed like P, and the conditional distribution of Y given X was given by W. Right. Let me restrict myself to uniform input distributions. For the binary case, it means that 0 and 1 are used both at probability 1/2. So P is always going to be uniform distribution, in which case I can get rid of that also. Okay. So let I of W denote I of xy when the probability of y given x, or maybe I should say P of xy is equal to half. I should maybe in general write the 1 over the cardinality of the input output uniform distribution for the x and W y given x. Okay. So joint is to x and y is like this when the input is uniform. Right. So in this particular case that we have, cardinality of x is 2. Let this be that. So now, let's not take a look at the I of W, let me take a look at I of W minus and I of W plus. There's a mutual information between U1 and Y1, Y2. There's a mutual information between U2 and Y1, Y2. Remember this W plus and this helping genie, so its output contains the symbol U1. So we have that. And note, by the way, also that the U1 and U2 are independent, so I can write this as being the I of U2, U1, which is 0. I use these channels with independent and uniformly superpoint flips, flip. Okay. Right. Plus, by the chain rule, like that. Okay. This is trivially true. So if we sum them up, what we find is the following. So I of if you sum this and this, what is that? That's the chain of expansion of the following thing. It's the expansion of the I of U1, U2, Y1, Y2. Right? The chain rule will say u1 and y1, y2 plus u2 and y1, y2 given the u1. That's exactly how the chain rule would work. But you also see the following thing. So the x and the u's are in one-to-one correspondence with each other. So this is the same as saying that the I of the x1, x2, y1, y2. Remember also that when the u1 and u2 are independent fair conflicts, so are x1, x2. If the u1 and u2 are independent fair conflicts, u2 is a fair conflict, u1 plus u2, since you add a fair conflict to a fair conflict, it is independent of the thing that you started off with. So this is equal to then the I of x1, y1, plus I of x2, y2, each of which are the same as IW. This is the mutual information developed over channel W, both of them. Equal to IW. So to see the following thing, this transformation that we have preserves the mutual information. I consume 2 copies of W to synthesize 1 copy each of W minus and W plus. But the mutual information of W minus and the mutual W plus that I created are exactly the same as the one that I have consumed. Okay? So this operation that is here is mutual information preserved. These 2 channels have the same. I haven't created, nor have I destroyed mutual information. Okay. Of course, I could have created, because of this U1 here, okay, that the channel output being U1, might have created mutual information, but we haven't. All right, good, fine. But have I made things any easier for myself or not? Because the whole goal of this transformation was the following. I was supposed to create these synthetic channels. I wanted 2 things from this operation. One is to preserve capacity. This is what this is doing here.